Okay, now we're going to apply the mean value theorem. Okay, now when you took Calculus 1, you got the mean value theorem, and that said I'm going to use uppercase F's here. That said that f prime of, now the textbook uses a C, so it's kind of something like that. So I'll use that same letter. It's a Greek letter. F of B minus F at A over B minus A for A less than that value C less than B. Now, so, all that's saying is I have, some function that does something like this. Okay, draw the straight line there. The right-hand side up here is the slope, m. And it says that in at least one place between A and B, so this is at A, that's at B, and at least one place, the derivative will be parallel to that slope joining the lines. And kind of visually, it looks like here there might be two spots where that happens, but there's always at least one. Okay, so that's the mean value theorem. Now, so if I say that f prime of x is equal to lowercase f of x, that's why I use the uppercases there, then the fundamental theorem of calculus that we also learned in Calculus 1 would say that this derivative, so here I'm just going to switch to that notation, so I get f of c is equal to, now uppercase f of b minus f of a, using the fundamental theorem of calculus, right? That's just the integral from a to b of f of x dx, and then divided by b minus a. Okay, so that is also a mean value theorem. Okay, it's just a different way to write it using the fundamental theorem of calculus. Okay, so that is the form of the mean value theorem that they're going to use. Well, and I should, right, A is less than C, less than B. Okay, so we have that. I think that's the only place I needed to write that. Okay, so we have that. Now, a reminder that, in our case, B is x plus h, and A is x, and so B minus A in this case is h. Okay, and we can move this so we can say the B minus A over to the left-hand side, but I'm going to switch sides here. So integral from A to B of f of x dx can be written as some f of c times h for A less than C less than B. So that's where they start with their mean value theorem. Now, so what that means is if we take the left-hand side of what we had, so we had C rho times A, integral from x to x plus h of u sub t s t ds. Okay, so we had that. So as I look at my mean value theorem here, right, there's our integral. And so I can, now the constants just come along for the ride, so they have to stick around. And then I'll get my integrand, u sub t, but at some c, and I'll put a 1 in this case. The reason I'm putting a 1 is because we've got another integral yet that we're going to do, so it'll have a different one. But it is true that this c1 is between a and b. So we have that from part of our relationship from the last video. Now we also, so that was the left-hand side, the rate of change of the total energy. Then on the right-hand side we had an integral, and that was the heat generated, and that was a from x to x plus h of our f of s and t ds. And so, whoops, and so that is a, comes along for the ride, and then f of some c2, because there's no reason to believe they're the same thing. Oh, and I wrote a s here. That should be a t. Not sure why I wrote a s up there. I just noticed that. That's a t. And then f of t, f of c2 and t. And again, a is less than c2, less than b. Again, these are different functions, so there's no reason to believe that those two values where the derivatives match the average value of the function, would be at the same place because they're two different functions. So, so we have that. Now, and the flux doesn't change because it was not an integral. Okay, so then writing these pieces, so I'm going to write this one, and then equals, and I'm going to put down the flux, that's that, and then plus the energy generated. Okay, so that becomes C rho A u sub t of C1 and t times h. Did I remember my h there? Oh, bad news. Yeah. See, this is, should have yelled at me through the video. Keep telling you people to do that. This is f times h. I forgot my h there, and I forgot my h there. Okay, so we have the rate of change of the total heat, right? But now using the mean value theorem, I can use this, and then equals. Now here we have the flux. That didn't change, so that was Ka times u sub x at the left. Sorry, at the right. Don't know my right from my left. X plus h comma t minus, and then at the left, u sub x, x and t. So there's the flux, and then plus that total energy, and that was our A times F at some C2 T times H. And in this case, A is less than both C1 and C2. Is less than B, and so we have that. They just wrote a single, they had the C1 and C2, but then they, for this inequality, they wrote a single one. I think that's a little odd, but then solving, okay, solving for u sub t. Well, so I'll divide everything by A. Well, everything has an A, so the A's will disappear. Dividing everything by the C in rho and H. Well, this has an H, so that H will disappear, but we'll keep the H on the underneath the flux when we divide. So we'll get our u sub t of C1, and in their case, they write a single C value, which is incorrect at this stage. So there's our K, but divided by the C rho, and times our flux. So that was the derivative with respect to x at the right-hand side. So that flux, but we want a net flux, so we're doing the subtraction. U sub x at the left-hand side, like that. But now that all gets divided by h. And then plus, and we have our 1 over C rho times F at C2 and T. And again, A is less than C1 and C2 is less than B. Okay, they ended up changing the C1 and C2 to the same. That's not correct yet. Okay, but now let h go to 0, or delta x go to 0. Well, when you do that, right, A and B are going to get arbitrarily close to each other. And so at that point, then this C1 and C2 would be exactly the same value, but we're going to call it just the x that we end up at as we let h go to 0, that original x. So this x, it's kind of the a here of our interval. It's that a. We're going to call it our x because that could be anywhere on the rod. And so we get u sub t at x and t. Okay, because again, if you squeeze, if B ends up heading down to A, then C1 and C2 have no option but to also head to A, which is the value x. And then alpha squared we use in place of that constant. And then here, notice as h goes to 0, well, we just get the second derivative with respect to x, because h is the x variable. And so that's where we get the uxx of x and t. Okay, this thing becomes that second derivative with respect to x. And then plus, and here they just take this whole term and call it uppercase f of x of t. Now, that's not the antiderivative. They're just saying it's this constant times that f. Okay, that's all they're saying there. But that is applying our mean value theorem to, and we use the fundamental theorem of calculus to this thing, and to get our solution. Okay. Now, I guess since this is also in that section, I'll keep going with their little bit down here. They introduced this 4.4, and so they say in their discussion they say okay, this completes the derivation of the heat equation, but then they say, well, before we close, suppose the rod is not laterally insulated and that heat can flow across the boundary at a rate proportional to the difference between the temperature of, at any given x and the surrounding medium. And they say that we keep at 0, okay? In this case, they're saying, so, not laterally insulated And so, you know, they have this rod. And now, instead of insulation, you got some sort of, here, bath at 0 degrees Celsius. Okay, then they say, well, the result is, and again, they're using that the heat flow in and out across the boundary is a rate proportional to the difference of the temperatures. So, you know, we would have something like beta, and then the difference would be U of X and T minus 0 in this case. So we would have that, so the 0 would just disappear, and they say, oh, well, then this becomes U sub T, and this is 4.4. U sub T is equal to the diffusion portion here along the rod, but then minus that diffusion across the lateral part of the boundary, and then plus the F of X and T. Okay, and this is beta is a rate constant with beta greater than 0. Okay, now that finishes up that section. We'll probably talk a little more about this. Maybe I'll mention it about the problems, because I think one problem is to show that this really is true, that under these assumptions that's what you would get. So I'll probably talk a little bit about that one to give you a head start on that question, I think. Okay, but for now, we'll call that done with this section.